The Python language was first created in about 1990 by a Dutch guy named Guido van Rossum, who is still pretty much the guy in charge of the language, but formal responsibility has been handed over to an organization called the Python Software Foundation. The Python Software Foundation effectively decides what's proper Python and what isn't. There are a few different implementations of Python, but by far the most popular is the one created by the Python Software Foundation itself, called CPython. So called because the CPython interpreter is itself written in C. When people talk about Python, they usually have in mind CPython. The other implementations like Jython aren't used nearly as much. Jython, as the name hints at, is a Python interpreter written in Java. IronPython is an implementation written for the .NET platform, and PyPy, very interestingly, is an implementation of Python written in Python itself. Just to be clear on that, it's a Python interpreter written as a Python program. One reason these three other implementations aren't used nearly as much as CPython is because they're less mature. In fact, they all lag behind in features. Jython, for example, doesn't include any of the features that have been added to CPython in about the last 4 years. A couple years ago, Python started a big transition from version 2 to version 3. And the big deal about Python 3 is that it not only added new features to the language, it actually changed some features of the existing language. So this means that code written for Python 2 in most cases won't run under Python 3, and vice versa. So code written for Python 3 won't run with a Python 2 interpreter either. Because of these changes, it's going to take a long time for code written in Python 2 to be updated to run for Python 3, and for some programs that in fact will never happen. So this means that the Python Software Foundation can't immediately stop development for Python 2. They have to still keep releasing new versions of Python 2. So it's almost as if Python 3 and Python 2 are actually separate languages. So far, the transition to Python 3 has been really quite slow. It's been almost 3 years now, and it'll easily take another 3 years before most new code written in Python is written in Python 3 rather than Python 2. As it stands, many people today still choose to start new projects in Python 2 rather than Python 3 because they need to use some piece of code which is written in Python 2 and won't work with Python 3. Despite all that, we're going to be covering Python 3, because I think Python 3, for one, is going to be the future eventually, and also, though it's by no means a radically different language, the changes are mainly quite small, the changes generally are for the best and make things simpler. So that's why I prefer to teach it. If at any point the need arises for you to work with Python 2, it shouldn't be hard at all for you to pick up on the differences after you've learned Python 3. So, what kind of language is Python? Well, it's nothing too surprising by now. It's an imperative language and it's dynamic, just like JavaScript and just like Pigeon. And in fact, semantically, it's very, very similar to JavaScript and also Perl and Ruby. The one big difference compared to JavaScript is that Python is a more explicitly object-oriented language, because Python has a formal mechanism for classes. To be clear, nothing in Python forces you to create your own classes, so you can write all of your code in a procedural style, but typically, most Python code is written in a mix of the procedural and object-oriented styles. So, jumping in, here's a snippet of JavaScript code, and here's the equivalent in Python. The first thing to note here at the top, comments in Python begin with a single hash character rather than 2 slashes as in JavaScript. And then in the next line, a function is defined starting with the reserved word def, short for define, rather than the word function. And the two other things to note about this function definition is that the header ends with a colon, and then the body of the function is written indented underneath, just like in Pigeon. We don't use curly braces to denote bodies, we just use indentation. And you can see the same thing in the if. The if header ends with a colon, and then its body is indented underneath the if. So Python syntax is indentation sensitive like Pigeon, not freeform like JavaScript, and as we'll see later, Java and C and most other languages have freeform syntax. In fact, Python is really the only major language which is indentation sensitive. The last couple differences to note here is that first, the condition in the if, x less than 3, doesn't require parentheses around it. And last thing to note here, in Python we can create local variables just by virtue of assigning to them. So here x, we don't have to declare that that's a local variable, it's just implicitly a local variable. As we'll see later, this actually creates a little bit of an issue when you nest functions inside others, just like you can do in JavaScript. Because that means in Python then, we have to, in some cases, explicitly denote that a variable is not local to that function, even though we are assigning to it in that function. Usually though, this isn't a problem, so it's just a nice little stylistic allowance that we don't have to declare our local variables. So, in summary here, you can see that in some ways Python is more like Pigeon, but in other ways it's more like JavaScript. Like in Pigeon, comments begin with a hash character, code is indentation sensitive, statements don't have to end with semicolons, and local variables and functions are implicitly created by assignment, but unlike Pigeon and like JavaScript, expressions in Python use infix notation rather than prefix notation. The basic data types in Python should be nothing surprising. They're basically the same things we saw in Pigeon and JavaScript. The only thing to note is that Python uses the terms lists and dictionaries, where JavaScript uses the terms arrays and objects, and what JavaScript and Pigeon call null in Python is called none. And yes, it's written always with a capital N, which is actually kind of aggravating because that makes it harder to type. Every data type in Python is a class, and for every class there is an actual object representing that class. So here in the diagram, each of these represents an object, which is a class. Bool here is the Boolean class, str is a string class, int is the integer class for integer numbers, list for lists, dict for dictionaries, and function obviously for functions. And like in a lot of object-oriented languages, the classes in Python are arranged into a hierarchy with a class called object at the top. So the arrows are indicating here that, for example, the bool class is a direct child of the object class. When you create your own classes, they will by default directly inherit from object. So the class Natalie here is a child of the object class. You may, however, specify that your new class inherits from some other class. Say here Aaron inherits directly from Natalie, and Roy is inheriting directly from the int class. Notice though that for any class you create, object is going to be the ultimate ancestor. This makes sense though, of course, because anything you create is a kind of object. Keep in mind that the idea of a class is we can produce from it other objects which are instances of that class. And in fact, every object in Python is an instance of some class. So what about class objects themselves? Well, the answer is that they themselves are instances of the type class. I suppose Python could have called it the class, but they decided that was confusing. Actually in Java, that's what they chose to call it. In Java there's a class, but in Python there is a type class. So what's really confusing here is the relationship between type and the object class and the other classes. As the arrow from type to object here is indicating, type is a direct child of the object class, but that's just the inheritance relationship between these classes. Type is a child of object, but very strangely, the object class is itself an instance of the type class, and also it's an instance of itself. So think about this. The object class object itself is an instance of the type class, because the object class is a class. However, the object class is also an object, so it is also an instance of itself. And then the converse is true of the type class. The type class is an object, so it's an instance of the object class, but it's also a class, so it's an instance of itself. So let me just repeat that. Object and type are instances of each other and also instances of themselves. So object and type have this weird incestuous relationship. The same is actually true for every class object. Every class object is an instance of both the type class and the object class, because they are both classes and they are objects. But for every object which is not a class, that object is just an instance of its class, and then indirectly they are instances of that class's ancestors. So, for example, if we create a function, that function object is an instance of the function class, and in turn it is also an instance of the object class. And say, if we create an Aaron instance, that object is an instance of the Aaron class, and in turn an instance of the Natalie class and the object class. To create an instance from a class in Python, we invoke it like a function. So here, for example, assuming Natalie is a reference to the Natalie class, then if we invoke it like a function, this expression returns a new Natalie instance. Now, we can do this with any class, but of course for some of the built-in classes, like say function, we wouldn't create functions this way. To create a function object, we use a def statement. For any class, though, which isn't built into the language, this is what we use. Most objects in Python have what in JavaScript we call properties, but Python calls attributes. You should recall from JavaScript that when you look up a property on an object, if the object itself does not have a property of that name, JavaScript will follow this special link from that object to another object, and it'll keep looking up the chain until it finds a property of that name. A similar thing happens in Python, except the search follows the chain of inheritance through the classes. So here, for example, we have an Aaron object, which is an instance of the Aaron class, which itself inherits from Natalie, which in turn inherits from object. If we try to get an attribute named foo from the Aaron object, Python first looks in the Aaron object, and if there is no such attribute of that name, Python then looks in Aaron. Failing there, it then looks in Natalie, and failing there, it looks in object. And if object doesn't have any attribute of that name, Python will throw an exception. Things work slightly differently when we look up an attribute on a class object. If we look up an attribute foo on the Aaron class here, Python first, of course, looks in that Aaron class, and failing to find it there, it then looks in the Natalie class, and then it looks in the object class. But then, unlike with an attribute search on a non-class object, Python will look in the type class. This makes sense because Aaron, a class object, should have all the things which type has. And so when we look up attributes on Aaron, we expect to find the stuff which is in the type class. This attribute search behavior is the essence of the relationship between instances in their class and classes and their parents. When I create a class Aaron which inherits from Natalie, the Aaron class and the Natalie class each have their own independent set of attributes, but when I look up something on the Aaron class or in an Aaron object, the attribute search will reach Natalie. So if the Natalie class, say, has a method named foo, but the Aaron class does not, invoking a method foo on an Aaron instance will invoke that method foo in the Natalie class. Likewise, if the Aaron class has an attribute bar, which is assigned a function, then if we invoke a method bar on an Aaron instance, that Aaron instance doesn't have to have its own function bar. When the attribute search for bar doesn't find anything in the Aaron instance itself, it'll look to the type, it'll look to the Aaron class. For fields, though, it's a different story. When we create instances of class, each instance should have its own fields. So say, if Aaron objects are supposed to have a field named X, then every Aaron instance should have its own attribute named X. Now, it's not the case that every object in Python has attributes which we can assign to and retrieve. First off, the attributes of the built-in classes, such as object and type, can't be modified. If you started messing with these classes, you'd very likely break the whole language, so Python simply doesn't let you do it. It's also the case that for some of the built-in types, their instances don't have any attributes at all. So, for example, while the string class and the number class and the list class all have attributes, the instances produced from those classes do not. This effectively means we can never assign to an attribute of these instances because they don't have any attributes, but it doesn't mean we can't look up attributes on these instances, because when we do so, the search for that attribute will of course not find the attribute in the instance itself, but it'll look for the attribute according to the normal search rules. It'll look in the class and then up the chain of inheritance. So here, for example, the string literal hello, that's a string instance which we assign to the variable x, and then if we write x.foo equals 3, that's attempting to assign 3 to an attribute foo of that string instance, and that's not legal, so this will throw an exception. But it does make sense to write x.upper because upper is an attribute in the string class. So x.upper here will retrieve the value of that attribute in the string class. Recall that in JavaScript, writing x.foo is basically just a shorthand syntax for writing x and then in square brackets a string foo. This is not the case in Python. In Python, dot is the only way to access attributes, and the square bracket operator is a totally different operation. Square brackets are used to retrieve and set the key value pairs of dictionary objects. A dictionary in Python is an instance of the dict class, and when we look up values in a dictionary, there is no concept of a search order. The search is done just in that dictionary itself, not in any other object. So the intention in Python is that you don't just use any object with attributes as a grab bag in which to stuff a bunch of key value pairs. For that purpose, you're supposed to use a dictionary. It's really kind of weird how JavaScript does it, where these objects are used both as collections and then also to represent data types organized into a hierarchy of inheritance. It's clever how they only have the one simple mechanism to cover both those bases, but it's just weird. To make what's going on in Python clearer, let's look at dictionaries. First off, to create a dictionary, we can simply invoke the dictionary class called dict. This returns a new empty dictionary. More commonly, however, we create dictionaries with curly braces, just like we create objects in JavaScript. So here, this empty pair of curly braces, that returns a new empty dictionary, and then the second pair of curly braces has two key value pairs. The first with the key string of foo and the value 3, the second with the key number 4 and the value 12. Two differences from JavaScript to note here. The first is that the key string foo must be written explicitly as a string. We can't just leave off the quote marks as we can in JavaScript. If we were to just write the identifier foo here, that would be the variable foo. So the key value pair here would be the value 3 with the key of whatever is in the variable foo when this dictionary was created. The other difference from JavaScript is that Python dictionaries can have keys which aren't strings. So whereas in JavaScript writing 4:12 would represent a key value pair of the string with just the character 4, here in Python this is a key which is actually the number value 4. So as mentioned, to retrieve the values from a dictionary or to set key value pairs, we use the subscript operator, the square brackets. Here we're creating a dictionary with 3 key value pairs and assigning it to x, and then in the next line the expression x subscript 56 retrieves the value of the key 56, which here is 11. And then in the next line, when we write x subscript string orange and assign it 14, that is assigning a new key value pair with the key of the string orange and the value 14. And then in the last line, we're assigning another key value pair. This time the key is -30, and the value is a new empty dictionary. So to reiterate, the subscript operator, the square brackets, is used just to set and retrieve key value pairs from dictionaries. It is not used to retrieve or set attributes of objects. However, the subscript operator is also used with lists to get and set the items of that list. So very briefly, we can create a new list object by invoking the list class that returns a new empty list, or more commonly we just used square brackets just like we did in JavaScript to create what it calls arrays. Here we are assigning the variable x a new list with 3 items, first 67, then none, and then a string George Washington. And in the next line, the expression x subscript 0, that returns the first item, 67 in this case, and then if we write x subscript 2 equals the string hello, that is reassigning the third slot in the list. So previously it had the string George Washington, now it has the string hello. Unlike with JavaScript arrays, we can't assign out of bounds on a Python list. So here when we write x subscript 3 equals 9, that's going to trigger an exception because index 3 would be the 4th item in this list. This list we created only has 3 items. If we want to add a 4th thing to this list, we have to first expand the list, and there are methods in the list class for doing that, which we won't cover here. We'll get to that stuff in the supplementary material. Let's look now at how method calls work in Python. The goal here is when we invoke a method, say x.foo, x somehow has to be passed as an argument to the method. So assume we have some class called Aaron, and that class has a function in an attribute named foo. If we then create an Aaron instance and assign it to a variable x, and write x.foo, that expression x.foo is looking for the attribute foo on the object of x, which here is an Aaron instance, and what it returns is not the function found in the class Aaron, but it takes that function and it wraps it in another kind of object called a method, and it returns that method bound to that object in x. This is a special behavior only for functions. In the class Aaron, the methods are expressed as just attributes which are functions, but then when we look them up via instances of that class, what we get back are method objects. What a method object consists of is simply a reference to the function and a reference to the instance, here x. When a method object is invoked, it invokes its function and passes on any of the arguments that were supplied, but it inserts the instance as the first argument. So here, when we invoke the method object with the arguments 3 and 5, that invokes the function from foo, but with x as the first argument. So the arguments to the function are x, 3, and 5. What methods are is really just an elaborate mechanism to somehow get that object before the dot, in this case x, passed as the first argument. When we create a class in Python, the convention is that any of the functions we give it for methods, the first parameter by convention expects to receive the instance. So when you see in code what looks like a method call, say x.foo with the arguments 3 and 5, what's happening is the expression x.foo first returns a method object, that method object wraps x and the function, and then the invocation of the method object causes the function to get called, with x as the first argument, followed by all the remaining arguments here, 3 and 5. Now, it turns out that most of the operators in Python are really method calls in disguise. For example, x plus y, Python implicitly translates that into an invocation of the method add with 2 underscores on both sides. And the first operand of the plus sign becomes the instance of this method call, and the second operand gets passed into the method. So x plus y becomes x dot underscore underscore add underscore underscore with the argument y. And it's the same idea for the other arithmetic operators. Subtraction becomes sub, multiplication becomes mul, division becomes div. And the reason for the underscores is that Python has a convention whereby any attribute name which is generally not meant to be accessed directly, such names by convention start and end with 2 underscores. So the intention generally is that the add method here is not invoked directly, rather we invoke it by using the plus sign operator. Now, usually when you use arithmetic operators, you use them on numbers. So imagine here that x is a number, it's an integer. And so the method add here is being invoked on an instance of the integer type, int. If you look in the int class, you will find these attributes. You will find underscore underscore add underscore underscore, you'll find sub, you'll find mul, you'll find div. It's the functions of these attributes in the int class which get invoked when we use the arithmetic operators on integers. Now, you're probably wondering 2 things. First of all, if the addition operator ultimately invokes a function, what happens in that function to do the addition? Because that function just can't use the addition operator, because the addition operator would call that function again. It doesn't make any sense. That would be circular. So the answer here is that the integer class has functions which are specially created by the interpreter. They're not regular Python functions. They're what are called built-in functions. They don't contain Python code, obviously. In the CPython implementation, for example, these functions likely contain C code. So that explains that mystery. The other very puzzling part about these operator methods is why have them at all? Why not just define, say, the addition operator, the plus sign, to directly do addition? That's how it's done, say, in JavaScript, so why doesn't Python do the same? Well, the idea is that if operators really invoke methods, that means when you create your own classes, you can define methods of these names, like say add, and thereby give instances of your class defined behavior with the standard operators. So if our class Aaron has a function in its attribute underscore underscore add underscore underscore, and that function takes 2 arguments, then that gives Aaron instances defined behavior with the plus sign operator. So if you write x plus y, where x is an Aaron object, that'll work. It'll invoke the add method of the Aaron class. Now the question still is, what the hell really is the point of this? Why is it so great to have your own classes work with the standard operators? I, for one, think it's really quite pointless. It's really just making a stylistic allowance, whereby in certain circumstances you may make your own data types work with the standard operators. And for whatever reason you don't like the idea of giving that operation a standard attribute name and invoking it like any other method. A better argument for this arrangement, though, is that it gives the language pervasive polymorphism. If method calls can be polymorphic, they can change based upon the arguments and the type of the object, well then why shouldn't operators also be polymorphic? Whether or not you object to this feature, it does exist, and it applies not just to these arithmetic operators, it applies actually to most operators, including the subscript operator on dictionaries and lists we saw earlier. So when you get or set items, say, from a dictionary, those are really method calls in disguise. They are called getItem and setItem respectively, both surrounded in double underscores. But for now, we won't enumerate all of the different operator methods. We'll save that for the supplementary material. Now, actually, there is one last thing we need to say about these operator methods, and that is that the attribute search behavior gets slightly modified when using these operators. For example, say again we have a class Aaron and we have an instance of Aaron A. And then we do an attribute lookup for __add __. Well, because we're looking up the operator method explicitly by name, this is done like a regular attribute search. First, Python looks in the Aaron instance object itself, then it looks in the class Aaron, then in its parent, all the way up to object. However, when we use one of the operators which implicitly translates into a method call, the attribute search behavior slightly changes. So here, when we write a plus b, that's implicitly invoking a dot __add __ with an argument of b. So the attribute search for that __add __, the search doesn't start, as usual, in the Aaron instance itself, rather it starts directly on the class. So the special rule for these operator methods is when invoked via the operator, the attribute search skips the instance itself. Now, 99 times out of 100 when you invoke a method, it doesn't matter if you skip the instance itself because methods are generally attached to the classes, not the instances. In the case of these operators, we know that the attribute search is looking for a method, not any other kind of attribute, so it's safe for Python to skip the instance. That's one reason Python does it. There's a small little efficiency gain in that it doesn't have to search first in the instance. The real reason for this rule, though, is that when we use an operator on a class object itself, we don't want the operator method to be found in that class itself. So for example, if Aaron itself had a method called __add __, and we invoked Aaron with the addition operator, don't ask me why you would do this with a class, but if you did, you wouldn't want it to be found in Aaron itself, because when Aaron defines an add method, that's for instances of Aaron, not for the class Aaron itself. Now, I will say that defining behavior for standard operators with class instances is already a questionable thing to do, but it'd be really weird to do the same for classes themselves. However, there are a few operator methods defined in the type class, such that there are some operators that work with classes as part of the standard behavior. We won't discuss that stuff now, though. We'll save it for the supplementary material. Finally, let's look at how to actually create your own classes. Classes in Python are created with class statements. Class statements superficially look a bit like function definitions. Instead of def, you have the reserved word class, and then you put the name to which the newly created class object will be assigned. Here, the name is Jack. And then following that in parentheses, rather than an argument list, we put simply an expression which returns a class. This becomes the parent of the new class we are creating. So here in the parentheses, we have an expression of a variable Kate, presumably referring to the Kate class. And then after the parentheses, the header ends with a colon, and what follows is a body of code. This body of code gets executed once when the class is created. So be very clear on that. When you define a function, the body of the function is not executed when the function is created. It's only executed when the function is invoked, and that may happen many times. Here, the body of the class executes when the class object itself is created, and that only happens the time the class statement itself executes. Now, the body in this class, what happens is it can contain any code we want, but any names we assign to in the class body get added as attributes to the class object. So, in this class statement, a class object is being created, which inherits from Kate. That class object has two attributes, one x with the value 3, and the other named whale with a function object. And once created, that class object itself is assigned to the variable Jack. Notice that the function here, whale, its first parameter is called self. That's a convention of Python classes. Because the function in this class is going to be effectively a method, the instance object should normally get passed in as the first argument to the function, and the convention in Python is to refer to the instance in methods as self. If you create a class and don't specify a parent class, implicitly the new class will inherit from object. Actually, in these cases, you don't have to write the parentheses at all. We can simply omit them. In any case, now that we have our class object, we can create instance of this class by simply invoking it. But now, what about constructors, and what about giving our instances their own fields? A class in Python is effectively given a constructor by giving it a method with a special name, init with double underscores. When we create a new instance, Python will implicitly invoke this function as a method on the new instance. So now in this example, when we instantiate Jack, the new Jack object gets passed to self in the init function. And so when 4 is assigned to the attribute foo of self, that's giving the new instance an attribute foo with the value 4. That's how in Python we get constructors and fields. The init function acts as the constructor, and in that constructor you can give the instance fields by assigning it attributes. Now, for many classes, we want the constructor to effectively be parameterized. We want to supply input when we create instances. We can have this in a Python class if we simply give init more than one parameter, and then when we instantiate the class, we must provide arguments to pass to these parameters. So here, when the init function has parameters a and b in addition to the first one, self, and we instantiate Jack with the arguments 8 and 4, well, per usual, the new Jack instance is passed to self, but 8 here is passed to A, and 4 is passed to B. So when we add A and B, we get 12, and so 12 is assigned to the attribute foo of the new Jack object. Now, in the parentheses where we specify the parent class, we can actually specify more than one because Python supports multiple inheritance. It's possible for a single class to have more than one direct parent. Here the class Aaron has two parents, Natalie and Jack, and notice they're separated by commas. The question this raises is how does it affect attribute searches, because attribute searches are the essence of the inheritance relationship in Python. Well, the rule for this turns out to be slightly complicated, so I'll give you just the brief version, which is that the search is done breadth first rather than depth. So in this example, the attribute search goes from Aaron to Natalie, and then to Jack, and then to the parent of Natalie, Simon, and then to the parent of Jack, Kate, before finally going to object there at the top of the hierarchy. The alternative to this search behavior is if Python were to do depth first rather than breadth first. In a depth first search, Python would check Natalie and all of its ancestors before it would even look at Jack and its ancestors. Actually, depth first is how Python did this search in earlier versions. In Python 3, however, it's always breadth first. And lastly, do note that it matters the order in which we write the classes in the parentheses. So here, because Natalie is listed before Jack, the attribute search checks Natalie before it checks Jack. Fortunately, in practice, multiple inheritance just isn't used all that often. One reason being that it's simply just kind of confusing. The other reason being that generally it's not all that useful. However, Python, unlike some other languages, does allow for multiple inheritance. Each file of Python source code is called a module. For every module which is run, the Python interpreter creates an object to represent that module, and as that module executes line by line, any names that get assigned at the top level of the module, that is, any assignment which is not inside a def statement or class statement in that module, those assigned names get added as attributes to the module object. So, once a module finishes executing, we're left with this module object that contains attributes for everything that was assigned in that module. This is how you can have multiple modules tied together. Within one module, if we want to invoke, say, a function defined in another, we just need to access it as an attribute from the module object representing that other module. Consider this example. Say we have two files of Python source code, one called april.py, the other called june.py. In the April module, two names get assigned to at the top level. First, a variable x is given the value 3, and then the def statement creates a function object which it assigns to the variable foo. So the April module object ends up with two attributes, x and foo. Over in the June module, we can access the April module by importing it with an import statement, which we'll explain more in detail later. But in short, what happens with the import statement here is first Python looks for a module called April. If that module has not yet run, Python will execute that module and create an object module for it. And then back in June, the import statement is implicitly an assignment. In the module June, the name April is being assigned the April module object. So then in the next line, when we write april.x, that returns 3. And if we write april.foo, that returns the function foo defined in April. If, however, we write april.y, well, the April module has no y attribute, so this will throw an exception. When we start the Python interpreter, we need to specify one module for the interpreter to run, and that module runs, and in course of doing so, it may import other modules, thereby causing them to run. It may happen, though, that a single module needs to get imported by multiple other modules, and so in the course of running, a single module may end up imported more than once. When this happens, though, the interpreter will only actually execute the module the first time it is imported. For all subsequent imports, that import simply uses the existing module object. So at first it may seem that a module is sort of like a function. It's this piece of invocable code, but it's really not like a function because it's guaranteed by Python only to run once in the course of that program. And also, of course, unlike functions, modules don't have parameters and they don't return a value when they're done executing. I mentioned briefly before that local variables in a function of Python get created implicitly by assignments. Recall, though, how things work in JavaScript. In this JavaScript function, x here is a local variable because the function foo has a parameter named x, but the variable y here is not local because the function foo has no parameter named y. To make it a local variable, we have to explicitly declare that this function foo has a local variable y with a var statement. In the Python version of this function, again, x is clearly a local variable because there is a local parameter x, but y is also a local variable just by virtue of the fact that we assign to y in this function. That raises the question then, what if in the function you want to assign to a variable which is not part of the function? Well then, we have to do the inverse of what we do in JavaScript. In Python we have to explicitly declare that a variable is not local to the function. And one way to do that is with the global statement. Here, the statement global y is declaring that in this function, y refers to a global variable. Global here meaning really a variable of the module. So now the assignment of 3 to y is assigning 3 to y of the module, not a local variable y. There is no local variable y in this function. Now, be clear that in cases where you just need to use a non-local variable, you don't need to declare that variable as non-local. You can just use it. And as long as you don't assign to a variable of that name in that function, Python understands that it's not local. So here in this function, if you write y assigned to x, well, x of course is local, but y isn't, as long as there's no y being assigned to in this function. Again, recall how JavaScript treats variables in nested functions. Here in the function bar, the interior function, when we assign it to y, the function bar doesn't have its own local variable y, so this must be something from the enclosing scope. In this case, it's y of the immediately enclosing function. If we want y in bar to be a local y, we have to declare it as such with a var statement. In Python, in contrast, when we don't explicitly declare that y is non-local, it's assumed to be local just by virtue of the fact that we are assigning to it. If you want y in the function bar to actually refer to y of function foo, you have to declare it as such with a non-local statement. The non-local statement tells Python that this variable belongs not to this immediate function, but to some enclosing function. If instead of declaring y as non-local, we declared it global, that would mean that y in the function bar refers to y of the module, not y of the enclosing function. So, to sum up the rules, if a name is assigned to in a function, it is then a local of that function unless it is declared to be global in that function or non-local in that function. The difference between the two being that global makes it a variable from the module, while non-local means it must be a variable from some enclosing function. Now, a subtle but important rule to keep in mind is that when you declare something non-local, there must actually be a variable of that name in an enclosing function. If there is no such variable, Python considers that an error and will throw an exception. Understand, though, this is only the case with non-local. If you declare in a function a global variable which doesn't actually exist in the module, that's perfectly fine, because when in the function you actually do assign to that name, it will create the module variable of that name if it does not yet exist. That's a reasonable thing to do with modules because names assigned in modules are really just attributes added to the module object. It doesn't make any sense to do the same thing with non-local variables because how would you add a new local variable to some enclosing function? It just doesn't make any sense. So that's why Python has the double standard. When you declare a variable to be non-local, Python requires that such variable actually exist in an enclosing function. The body of a class in Python is considered its own scope, but classes aren't really like functions. The variables we declare in classes become attributes of the class object. They're not really local variables. And moreover, classes have no concept of closure, so it's really a quite different thing going on in classes than compared to functions, even though they are both scopes. And it is possible, of course, for a class to be nested inside a function, or to be nested inside another class, or to have other classes and functions nested within it. But the odd thing with classes is that any scope nested within a class cannot see the scope of the class itself. So here, for example, in this class Stephen, we are declaring a function foo, and that function definition of foo is itself its own subscope of the class Stephen. Inside that function, we can't directly refer to anything in the scope of the enclosing class. So here in the function when we return Mark, presumably meant to refer to Mark assigned in the Stephen class, this actually doesn't work because Mark of the Stephen class is not visible. So the way around this is in the function we can refer to Mark indirectly via the reference to the class object itself, because the class object is assigned to Stephen in some enclosing class, which the function can see. So Stephen.mark will work. That assumes, however, that Stephen itself is not created directly inside another class, which would be an odd thing to do, but it is legal. So here, when Stephen is being created inside Kelly, so Stephen becomes the only attribute of the Kelly class, inside that function foo to refer to Mark, we now have to write Kelly.Stephen.mark. Here we have to assume Kelly itself is not declared directly inside some other class. We have to assume it's, say, part of the module or created in some function. Because, again, the rule is that inside a scope, you cannot see the scope of any enclosing class. Because a class is a kind of scope where assignments to names implicitly become parts of that scope, this means we have to use the non-local and global statements if we want to assign to a name in that class body and have that name refer to something from an enclosing scope or the module scope, rather than refer to an attribute of the class. This in truth would really be an odd thing to do, but I mention it really just for completeness and to drive home really how the scope of a class body works. Python includes an important special module named built-ins, so called because it includes dozens of commonly used built-in functions and classes, such as, say, the print function, which prints text on the console, a function called abs, or for absolute, which returns the absolute value of a number, or, say, the classes like stir and object. These things are all placed in the built-ins module. If you were to import built-ins, that would assign to the name built-ins the built-ins module object, and then if we write built-ins.print, that would get us the function print from the built-ins module. And so here if we write built-ins.print with the argument 3, that would print the number 3 on the console. The special thing about the built-ins module, however, is that we can access its attributes directly. We don't have to import it. So rather than writing import built-ins and then built-ins.print3, I can simply write print with the argument 3. The reason this works is because when you use a variable name, Python searches for that name first in the local scope of where we are, say if we're in a function, and then if it's not found there, it'll look in the enclosing scope, say any enclosing other functions, and then if it's not found in any of those, it then looks in the global scope, aka the module scope, the module, and if it's not found there, it'll then search in the built-in scope. So in Python, we call this the rule of LEGB, local enclosing global built-ins. When Python needs to resolve a name, first it looks in the local scope, then the enclosing scope, then the global scope, aka the module, and then the built-ins module. The local enclosing global part you're already familiar with. That's basically how JavaScript works too, but the thing Python adds is that it then goes and looks in this fourth place, the built-ins module. So again, generally when we want to access an attribute of the built-ins module, we don't access it per usual as an attribute, we just refer to it directly by name. Now, the way this works does mean it is possible to effectively obscure names from the built-ins module. For example, if in the current module we were to assign to the name print some value, say here the value 9, now if we try and invoke print as a function, well, print isn't going to be found in the built-ins module, it's going to be found here in this module itself, and we're going to get an error here because you can't invoke a number as a function. Generally, Python programmers solve this problem by simply avoiding assigning to names found in the built-ins module. An interesting thing to note here is that this is the only case where it's possible for the use of a variable name to actually change which scope it resolves to. Imagine, for example, that in some function we invoke print. As long as that function itself and none of its enclosing functions and its enclosing module have no variable themselves called print, that print in the function will resolve to print of the built-ins module. But because modules are mutable, that is, attributes can be added and removed, it's possible for that print in the function to change what scope it resolves to. If we add print to its enclosing module, then that print in the function will no longer resolve to print of the built-ins module, it will resolve to print in its enclosing module. And in fact, the reverse can happen as well. If a name resolves to something from the enclosing module, if we delete that attribute from the enclosing module, then it might resolve to something of the same name in the built-ins module. So in short, it's possible for a name that resolves to something in the enclosing module to switch to resolve to the same name in the built-ins module, and vice versa. The switch can go the other way. This does not happen with the local variables of functions. The local variables of functions are effectively fixed in which scope they resolve to. Very briefly, we can see this happening in action. Here's a function foo, which invokes print from the built-ins module, and if we invoke foo the first time, that's okay, it prints hello, but then if in that module we assign to print some number, something which is not a function, and then we try and invoke foo, well then print inside the foo function is going to resolve to print of the local module now, and that's a number, not something we can invoke, so this is going to trigger an error, it's an exception. So finally now, if we wanted to create the Hello World program in Python, it would simply be a module, a single source file, consisting of just this line, print with the argument Hello World as a string. When we run the Python interpreter and we don't specify any module to load and run, Python then runs in interactive mode. In interactive mode, Python gives you a prompt at which you can type a statement of code, and then you hit enter and Python will run that code. Effectively, interactive mode is like as if we are writing a module of Python code line by line, and every time we hit enter, it runs that code immediately. The utility of this isn't really all that great. I do, though, like to use Python as my calculator, and this interactive mode does come in handy for people learning the language because it's nice that you can just start up the interactive mode and try a few things and see what happens. Notice here in this interactive mode, when I wrote a line that triggered an exception, normally an exception that isn't caught in Python will basically abort your program, but here in the interactive mode it simply just prints out the exception message and then lets you continue on to type more statements. The last thing we'll talk about in any detail here is how Python treats exceptions, which are basically the same as we saw in JavaScript, except a few terms have changed. First of all, what JavaScript calls a catch clause in Python is called an accept clause, and where JavaScript has a throw statement, the Python equivalent is called raise. In Python we usually say an exception is raised rather than thrown. The big difference in Python is that a try may have multiple accept clauses, and when an exception is thrown in the try, the except clause which executes is the first one which lists a class of which the exception object itself is an instance. So here in the example we have a try with 3 except clauses. The first except clause lists a class Amy, the second has 2 classes, Carol and David, and the third except clause doesn't list any classes, which means that it will match any exception. So if in the try block here an exception is thrown, Python tests whether or not that exception is considered an instance of the Amy class. So it must either be an instance of the Amy class directly, or it must be some instance of a descendant of Amy. And if that test proves true, if the exception is an instance of the Amy class, then that first except clause is the one that runs. Failing that, however, Python then goes on to test the subsequent except clauses. And so here it will test if the exception is an instance of either the Carol class or the David class or both. And if it matches either one of those or both, then that except clause runs. But then failing that, if we get to this last except clause that doesn't have any class specified, well, this except clause will match any exception object. So this effectively serves as the default exception clause. To restate all that, when an exception is thrown in a try, Python looks for a matching except clause in order, top to bottom, testing by type. And when a match is found, that is the except clause which runs. In a case where no except clause matches, then the exception will propagate. And finally, the last thing to say about exceptions here is that whereas in JavaScript an exception can be an object of any type, in Python exception objects must be instances of the base exception class. That is, they must directly be instances of that class, or they must be instances of some descendant of the base exception class. That aside, the big new idea with exceptions in Python is that an exception thrown in a try is matched to an except clause by type. That's the one big conceptual change. We have a few more things to say about exceptions, which we'll cover in the supplementary material. Now, in the supplementary material, we actually have a lot to talk about. There's a good 100 pages or so of material in there, really. And that's all because Python is actually quite a complicated language, especially compared to Pidgin and even compared to JavaScript, which is a real-world language. So very, very briefly, here's most everything we'll cover in that supplement. First off, truth value. Just like in JavaScript, where every object effectively has a truth value, not just the Boolean values of true and false, well, the same is true in Python. We'll talk about those rules. The logical, relational, and equality operators, those are the operators like and, or, greater than, less than, equals to, not equals. We have to discuss those in a bit more detail. Functions in Python can be declared to have special kind of parameters, and then when we invoke a function, we can supply the arguments in special ways. And these special mechanisms are, say, how we can invoke a function with some variable number of arguments, just like we can in JavaScript. A sequence in Python is a list or list-like data type, and a mapping in Python is a dictionary or dictionary-like data type. And in the supplement, we'll go over the many different operations which you can perform upon sequences and mappings. Then we'll talk about tuples, sets, ranges, iterators, and view objects. These are all different kinds of collection objects. A tuple, for example, is really just a list which is fixed, meaning you can't add, remove, or modify any of its items. The rest we'll explain in due course. We haven't discussed all the different ways you can write number literals or string literals in Python. There are a few different ways. And then there are rules in Python for allowing us to deviate from the rules of strict indentation. Like, say, you might have a very long function call where the arguments you want to spread them onto multiple lines. There's a rule that allows you to do that. We need to talk about number types because there's actually more than one number type. It's not like in JavaScript where you just have one type of number. There's actually a separate type for integers and floating point values. And then Python has a few additional handy constructs for doing control flow, such as the for and loop, and a few other things can have else clauses on them. And a del statement, del short for delete, is a statement beginning with the reserved word del, which we can use to remove things from lists and dictionaries, and also remove attributes from objects, and say remove variables from the current module. A lambda expression in Python is, oddly enough, the equivalent in Python of writing a function as an expression. Because recall, in JavaScript, we can write a function as either a statement, just like we do with the def statement in Python, or we can actually write it as an expression that returns a new function object. Lambda is Python's equivalent. It's unfortunately not as flexible and therefore nearly as useful as function expressions in JavaScript, and that mainly stems from the limitations of Python indentation syntax. This is actually the one thing I find regrettable about the indentation syntax. Also in the supplement, we need to go over the few dozen or so classes and functions found in the built-ins module, and then we'll explain exactly how the import statement works, and then we have what are called packages, which are basically bundles of modules, and then there's variations of import with the reserved words from, and also there are what are called relative imports. And then there's this very neat way of creating lists and sets and dictionaries called comprehensions. We'll explain those. Generators, as we'll explain, are effectively special kinds of functions which suspend themselves in the middle of execution and then later get resumed. Generator expressions are just a special way of creating generators. Destructuring is just a fancy term referring to this feature that allows us to conveniently assign items from collections, from dictionaries and lists, to variables. That's all it is, really. And then Python has what's called a with statement, which is mainly used in conjunction with files. In short, the most common use of with is it makes sure that when we open a file that we actually close it when we're done with it. And then the bytes type, that's effectively a data type which represents some sequence of bytes. And a byte array is just a variant which is mutable. The bytes type is immutable, just like strings are immutable. And then we will discuss all of the various methods found in the string class. There are many different useful methods there. And then finally, at the very end, we'll discuss meta classes, which are really a very kind of obscure feature of Python. They're really very weird. Basically, imagine a class for defining the creation of classes. They are really not used very often because they are really kind of weird, but we will cover them for completeness sake. And so that's everything pretty much we'll cover in the supplement. It's not light reading, but it's as short as I could make it. And all of that, though, including what we've already covered in this lecture, that's all just the language Python proper, the rules of its syntax and semantics. In practice, though, when you write actual Python code, you're going to need a lot of stuff found in Python standard libraries. Python standard libraries are really quite extensive. First off, you have these three modules, one called Math, one called Sys, and one called OS. Those are a good place to start. Math obviously has stuff for doing some basic math, like, say, trigonometry. The Sys module, Sys short for system, includes things having to do with getting information about the system environment, and OS, somewhat related, has to do with the operating system environment. And then beyond those three, you'll want to learn how to use regular expressions in Python. Regular expressions, if you don't recall, are a tool for doing complex search and replace operations in strings. And very importantly, you'll want to figure out how to do input and output on the console, how to work with files. What Python calls pickles, shelves, and marshalling, that all has to do with storing Python objects in a persistent state, that is, in some database or in a file, and then retrieving them, loading them in your program. You'll want to learn about how to deal with sockets for networking, how to do web stuff, like make an HTTP request, maybe deal with FTP and email. You'll want to learn how to use some library to interact with a database. And there are libraries for doing graphical user interfaces, GUIs. One popular one is called WX Widgets. There's another one called Qt, and a really ugly old one called Dekinter. And then, if you really want to get advanced, Python, or at least CPython, has a feature that allows you to create a Python module partly in C code. This is something you would do generally for efficiency reasons, because Python is not particularly good at, say, number crunching. C does that much more efficiently. So that might be something you wish to learn, how to write a C extension for Python. Though, of course, it's something you'd probably learn after learning C itself, which we'll do later.